Okay, we have built our first meta model. This is the meta model for the part of UML to represent classes, associations, and attributes. The concepts that I've just mentioned are reflected in the meta model insofar we have classes for attributes, for classes, for association ends, and for associations. So this first meta model has had 4 classes, and we described classes, attribute, associations, and association ends. Let us now consider also further concepts. Namely, we want to handle generalization between classes, and we want to handle association classes. We will, in this situation, apply invariance in order to achieve only valid class diagrams. In particular, for example, we will have restrictions on what is called generalization. And the invariance will then guarantee the following things. The attribute names have to be unique within the class. The attribute names and the association end names have to be different. When we use generalization, the hierarchies that we build are really hierarchies and they are acyclic. As an optional requirement, we can exclude multiple inheritance, as for example this is done in Java. So the overall result will be an extended class diagram. Extended in comparison to this class diagram because we want to represent generalization and association classes, and we want to specify more sharper things here with the invariance. So the overall result is a class diagram plus a stated invariance. And this combination of class diagram and invariance determines a set of valid object diagrams. And this set of object diagram builds the defined modeling language. The overall observation, the overall conclusion is metamodeling is an approach for language development. We have developed, as we will see later, when we have developed the class diagram plus the invariance, we have developed a particular modeling language. So this is the claim: metamodeling is an approach for language development. Now let us look at the details over here. This is our class diagram. These are the invariants. I've just taken the text of the invariance and put it here as a comment into an object diagram to have a nice textual visual representation here. So the class diagram is an extension of what we have seen before. Previously we have had attributes, classes, association, and associations. Now I have added the concept of a generalization, which is a reflexive association on the class, and it has the role subclass and superclass, sub and super, and both have multiplicities star over here. I want to be very general in the first place. And I have added here the association class, the ASSOC class, which inherits from class, and the ASSOC class inherits from ASSOC. So ASSOC class is a hybrid thing, has both aspects of a class and of an association. And now I'm adding invariance in order to restrict the possible object diagrams here. And now let us look at the content of the invariants that I have added. Yeah, within a class, the attribute names have to be different. Yeah, when I'm formulating here a class, it is okay that I have here an attribute name, which is a string, but it does not make sense to have a second attribute, which is also called name, and which is an integer. So the name of the attribute within a class is unique. And this is this constraint here for all classes C dot the attributes in the class, that's the role name over here. So I obtain all attributes of the class, and now I'm considering two attributes here in the particular class C, and when the attributes are different, A1 is unequal to A2, this implies the names of A1 and A2 have also to be different here. The association end names have to be different as well. When I have an association, for example, this reflexive association, it is not okay that I have on two spots here the same association end name. So when I have an association A and I'm considering the association ends, A is the assoc and I'm considering all the assoc ends, A dot assoc end, that's with this role name over here. When I have two different association ends, A1 and A2, then the two different association ends, A1 and A2, have to obtain different names. The attribute names have to be different from the association end names. Yeah, I do not want to have the situation that I have here an attribute called name and I have an association end name called also called name. Then when I'm now saying p.name, when I would have the identifier name over here, then p.name, I do not know. One does not know whether I'm referring here to the attribute or whether I'm referring to the attribute end. So the attribute names have to be different from the association end names. C is a class, C dot attribute, all the attributes in the class, that's this role name here, dot name. This is a collection of the names used for attributes, and I'm navigating here from the C over to the typed assoc end name, that's this role over here, and I'm considering the names of all these association ends. So this is a collection of strings, this is a collection of strings, and the intersection has to be empty. I cannot use the same name, the same string for a name of an attribute and the name of an association end. Concerning the particular modeling here with the assoc class is both a class and an assoc. And with this, the assoc class receives a name from the class and or via the class, and the assoc class receives a name via the association. And this constraint here guarantees that I'm doing here sort of a type conversion. I have here an association class AC, and then I'm converting the AC into a class C, and I'm converting the AC into an association A. Yeah, with these let statements here. And then I'm saying C.name is equal to AC.name. So when I have an association class, I'm considering the name as a class and the name as an association, and both have to coincide here. Yeah, concerning the acyclicity of the generalization, Yeah, it would not be okay if I introduce cycles in the generalization hierarchy. The generalization hierarchy in a class diagram should be acyclic. And this is done here with a closure operation that we have looked at in very much detail. So I have a class C, and I'm considering all the superclasses, and then I'm building the superclasses of the superclasses, and I'm building the closure. So C.super closure super are the superclasses and the superclasses and the superclasses and so on. And this should exclude C. And this is the requirement that when I'm going here into the super direction, this is an acyclic graph. And this is a respective requirement here. The last requirement is an optional requirement, as for example, this requirement is present in Java. In Java, there is no multiple inheritance, so we could require here no multiple inheritance for our modeling language as well. C.super size is less than or equal to 1. So this is really a restriction here. It's not we do not want the star, but we want to have here instead of the star, we are specifying here a 0.1. So we have no superclass or we have one superclass. This constraint could also be achieved by, instead of writing the star here, we could write the 0.1. So the overall result, as I've said before, we have a class diagram plus the stated invariance, and this determines a set of valid object diagrams. And this set of object diagram builds the modeling language that I have defined here with a class diagram and with these constraints over here. So I've really considered, I have used metamodeling as an approach for language description, for language development. Okay, this is an abstract, what I've presented so far is a simplification and an abstraction of what is going on in the proper UML 2.4 meta model. UML is defined by a class diagram plus some restricting OCL invariants, and this class diagram is called the UML meta model. UML was developed over the recent years by the object management groups. Various versions of the UML have been published. You see the different versions over here. A current and quite important version is version 2.4, an important and well accepted version of the UML. UML uses a different terminology, different class and association endnames than the motivating simple example model that I have used above. So UML does not use these class names and does not use these association names and does not use these association endnames. It has a different and more complicated terminology for specifying the UML. This is just an example. This was just an example to show to you what is going on, what can be done in a meta model, and it's okay for us that you consider this as something similar to the UML meta model. So what I will tell from now on, I will not ask about these details in an examination. What follows are some nasty details of the proper UML 2.4 meta model. So the difference in the proper UML meta model lies in the fact that attribute objects and association and objects are commonly treated as property objects. So UML does not distinguish between attributes and association and. A property object lives within a class. If a property object lives within a class, then it is an attribute. And if a property object lives within an association, then it is an association and. This lives in is the composition relationship, part-whole relationship. It is a black diamond. Here you see the proper UML 2.4 meta model. That is more complicated than the meta model that we have seen before. And this is the part of the UML 2.4 meta model that is needed to describe this simple class diagram. So you see here there are much more elements, classes and associations present in this meta model than in the simple meta model that we have had before, or even this simple meta model that was already capable of representing this class diagram. So the proper UML 2.4 meta model, it does not only have the class, it has the class classifier. Classifier has specializations, data type, class, and association. There is this class called property. So I said before, ASOC ends and attributes do not occur as different classes in the UML 2.4 meta model, but we have properties. And a property may belong to an association, and a property may belong to a class. By the way, here in the UML 2.4 meta model, you see exactly this phenomenon about the composition relationship, the composition part-whole relationship, that a class may be connected with a black diamond to a first container class, and it is connected to a second container class, and you have the 0.1 multiplicities here. And we have had that in the very first example. We have had here the homework, and we have had here the course, and we have had here the project. And then our conclusion was that a project, a homework cannot belong at the same time to a project, and cannot belong at the same time to a project and to a course. And here we have the property is exclusively either owned by an association, or the property is exclusively owned by a class. And you see here property and class are involved in generalization hierarchies. So we have here a sort of topmost element that's a named element, that's a class which has the name attribute, and the name attribute is then inherited to all subclasses over here. And the typing of an attribute is done here with a particular association between type and typed element, which are again both named elements and so on. And the property is a structural feature, and the structural feature is a typed element, and that's again a named element. And here we have, for example, that a class is a classifier, and the classifier is a type, and the type is a packageable element, and the packageable element is a named element. So this is there are also generalization is involved in the UML 2.4 meta model. And the representation of this class diagram in terms of an object diagram. So this is the we have had here the class diagram, and I have represented it as an object diagram which belongs to this meta model, and this was not the UML2.MetaModel, but this was my simple meta model for explaining what meta modeling is. And the proper meta model for this class model looks as follows. This is the complete representation of this class model as an instantiation of the UML 2.4 meta model. So what you see here, job is an association. Job has two properties, namely the employee property and the employer property. The employee property is typed by the person class, and the employer property is typed as a company class. And person class owns a property. The owned attribute is the person name, and company owns an attribute, the company name, and both are typed as string valued attributes. So this is the correct and complete UML 2.4 meta model object diagram to represent this class diagram. And you see here that the different role names, so the association owns association ends, association owns association ends, the role names over here, and the class owns attribute, owned attribute, owned attribute, class owned attribute over here. Okay, what follows here are a lot of details on the UML 2.4 meta model. In fact, what I have presented here are only the objects and the links. These objects have attributes in the UML 2.4 meta model, and the attributes are displayed over here. So again, the proper representation of this simple class diagram in UML 2.4 is this complete object diagram, because there are a lot of attributes which are defined in the class association, in the class property, in the class, and in the class data types, and you see the attributes over here. I will not go into the details here. I will just, it's sort of a warning message that the UML 2.4 meta model is much more complicated than what we have seen in the small little abstraction used for demonstration. These are the central elements of the UML 2.4 meta model. You see here, for example, what the elements that are used for instantiating person, job, company. The elements are class, which is a classifier, the element which is a type, which is a named element. Class is used for person and company. Association is used for job. A job has properties. An association has member ends, two ... member ends over here, and these are the employee and the employer. Well, in total, you see, and this is, for example, here the class to represent generalization, which is connected here again to the classifier, and it is again, it is much more complicated than the modeling that we have done for the generalization in the simple meta model. But this is not the end of the UML 2.4. UML 2.4 meta model has 63 classes, has 99 associations, has 54 invariants and 66 operations. The UML 2.4 meta model is available as a use model. When you look into the examples folder and into the example folder of use, you will find a folder with meta models, and there you find the UML 2.4 meta model, and it's a rather large use model, but it is available in use. And the fact that it is available in use, you see it over here. So I've loaded here the meta model into use, and there you see the message. You cannot read it, but you can speculate about it. 63 classes, and this is the really proper UML 2.4 meta model, and use is available. Use is able to load this model and to build instances. So this instantiation, for building this instantiation, I have loaded the UML 2.4 meta model, and I've built this here as an instantiation. In fact, this is available in as a plugin for use, and you can build. You can look at your class diagram in form of a meta object diagram, and you can construct also the relevant part of the meta model part of UML 2.4 that is needed for building your class model. So in reality, all things are more complicated, and there are also here some more classes and some been playing around with the meta models in that form that I've looked at the UML 2.4 meta model here from particular viewpoints. And yeah, we in the next part of this teaching unit, we will not go into these details of UML 2.4, but we will look into some behavioral meta models.